And okay, we are live. So, yeah, we can start. Please, Maria.
Sure,
Maria is our conductor. She will introduce our speaker and manage the whole thing, managing the questions after the
yeah,
lecture and everything. So, Maria.
definitely. Good evening, everyone. We're so happy to have you among us, and we're so excited for tonight's webinar. It's titled A Search for Life Beyond Earth, How It Works, Where It Stands, and Why It Matters, with our speaker, Bill Diamond. Actually, the topic tonight explores the science and technology of humanity's efforts to understand the nature and prevalence of life and intelligence beyond Earth and answer the questions: are we alone in the universe? For most of human history, I'm sorry, for most of human history, this fundamental and profound question has been relegated to the domains of philosophy or religion. But with our ascent to a technological species, manipulating the electromagnetic spectrum and having the capability to look for engineered phenomena coming from beyond our solar system, so-called technosignatures, the question of are we alone is now firmly within the grasp of modern science. In his presentation, Mr. Diamond will describe the scientific ways in which we seek to find evidence of life beyond Earth, the progress of efforts undertaken thus far, and the impact and relevance of these efforts to science and to society as a whole. So now I'm glad and happy to introduce our speakers. So Bill Diamond is a Silicon Valley technology veteran and current president and CEO of the SETI Institution in Mountain View, California. The SETI Institute is a nonprofit astrophysics and astrobiology research and education organization focused on the study of life in the universe. Prior to joining the Institute, Mr. Diamond had various executive management positions applied in technologies, most recently at the optical networking company Oclaro. Mr. Diamond has over 30 years experience in laser photonics and optical communication networks, X-ray imaging, and semiconductor processing technologies. His corporate background ranges from venture-backed startups to Fortune 100 multinationals, including CEO positions at Wave Splitter Technologies, then Slide Semiconductor in Singapore, and X-Radia, now part of Zeiss. He was also president of Comet Technology in USA, leading US operations for the Swiss Comet AG Corporation. Mr. Diamond holds a BA in physics from Holy Cross College and a master's in business administration from Georgetown University. He is also a past member of the advisory board for the McDonough School of Business Administration at Georgetown and is a current member of the Optical Society of America, the International Astronomical Congress, and the American Association for the Advancement of Science. He also serves on the board of directors of the Bay Area Science and Innovation Council, BASIC, in San Francisco. Mr. Diamond, you have the floor.
Great. Thank you, Maria. Appreciate that. And I'm sorry you had the long bio. The short bio would
Yeah, no,
have
no
been
worries.
maybe better, but it's wonderful to be here.
As much
And
as it takes to introduce you, no worries.
it's lovely to be here and have the opportunity to speak to you, your community, and greetings to everybody. I guess most of the audience is probably in Europe. So greetings from California to all of you. And again, thank you for this opportunity. So as Maria said, I'm going to talk today about the search for life beyond Earth and how we do it and what progress we've made and why we believe that this is an important endeavor and undertaking. So hopefully the takeaway will be an understanding of those items. And I do have some slides to share, so I'm going to attempt to do that now and share the screen. So hopefully that is working and you can see my slides. Okay, thumbs up. All right, so the search for life beyond Earth, this is the science, the technology, and the relevance of humanity's most profound quest. And again, I'm delighted to be here with the Space Renaissance International and be part of this Academy webinar series. It's a great honor to have this chance to speak with all of you. So we're going to talk about the search for life and intelligence beyond Earth. We're going to cover how it works and where it stands, why it matters, why it's important to us. And we believe ultimately that this is a journey of ultimate discovery, that this discovery would be among the most profound in human history, to learn that there is life beyond Earth, potentially even intelligent and technological life. Certainly this would be an extraordinary discovery. And yet also the journey of getting there is also somewhat extraordinary. So there's three big science questions in the line of work that we undertake, which I think are big science questions for all of humankind. And that is, first of all, how does the universe work? So what about the Big Bang, and how did we get from the Big Bang to having galaxies and stars and planets, and at least life on one planet that we know of, that being our own planet Earth? So how did all of that happen? How does it work? And how did we get here? So what are the conditions that gave rise to the possibility for life? And how did life begin on Earth? What are the origins of life? And then, are we alone is the third question. Have the conditions that led to life on Earth arisen anywhere else in the universe? And if so, can we find evidence of that life on other worlds? And do we have the technology and the means to look for it and discover it? And so those are the big science questions that we are pursuing. But they're not just our questions at the SETI Institute or indeed at other institutions. These are, in fact, the three top science questions for NASA. So if you were to go and Google what are the NASA's science objectives, particularly, these are the three primary questions that are driving NASA scientific research. What's interesting is, and Maria pointed this out in the abstract, that at this point in time in human history, we actually have the tools and the technology to answer that question. We can no longer just have that question of are we alone in the universe be something that philosophers can ponder or religious individuals, or we can just imagine. We actually have the ability to scientifically pursue this question and make discoveries. So that is, I think, a very profound moment in human history that we are in now. And it's only quite recent that this has been the case. So a little bit about the SETI Institute itself. As an organization, we have a pretty straightforward mission. It's to lead humanity's quest to understand the origins and the prevalence of life and intelligence in the universe, and to share that work with the world. And that second part is very important, integral part of our mission, because we are both publicly funded in terms of receiving grant monies for research and education programs from NASA and other federal agencies. We are also funded through private foundations and private philanthropists and individuals. But in all cases, it is our responsibility, which we take very seriously, to share the work that we do with everybody. To make the work that we do known, primarily through outreach programs and education programs, and to share the progress we have with everybody across the world. So that's what we set out to do. And we do this under three organizations. So we have the Carl Sagan Center for Research, which is about exploration and science. We have the Center for Education, where we do education programs for teachers, for informal direct students, such as Girl Guides and Girl Scouts and Boy Scouts and things of that nature. And then we have outreach, which is our website, our social media, lecture series and talks, and other direct public engagement. And that's to inspire everyone with the kind of science we do and the kind of questions that we're pursuing. So that's our organizational structure. And we have a really interesting history of personalities associated with the Institute. We were founded by Dr. Jill Tarter, who is a noted astronomer in her own right. And if anybody out there saw the movie Contact, which I think was a good 20 or so years ago at this point, Jill Tarter was the inspiration for the character played by Jodie Foster in that movie, Ellie Arroway. And in fact, for those of you who've seen it and recall the opening sequences of Ellie Arroway as a young radio astronomer taking place at the Arecibo Observatory, this big dish radio telescope in the mountains of Puerto Rico that sadly has since collapsed, but is iconic. It was in the movie GoldenEye, and it's had other roles in cinema as well as in science. But Jill conducted radio astronomy and SETI programs there, just as Ellie Arroway and Jodie Foster did in the movie Contact. And that's because Jill was working with Carl Sagan at Cornell University. Carl Sagan is the author of the book Contact and an astronomer in his own right. Dr. Frank Drake was the first chairman of the Institute, and he's famous for something called the Drake equation, which you can Google and look up, but which we will also describe later in this presentation. So we'll come back to Frank and his formula, which has been very central to the role of the SETI Institute and even NASA for many years. Baruch Blumberg was at NASA for a number of years, a Nobel laureate in medicine, actually, for his work on the hepatitis vaccine. And Charles Towns is another Nobel Prize winner who was on our board. He invented the maser and the laser, so he won the Nobel Prize for those developments some years ago. Both Baruch and Charles and even Frank have now passed away. Jill is thankfully still with us. And then Carl Sagan was also on the board of the Institute. Carl was very famous in the United States for a television program called Cosmos that really opened up to the whole public the idea of space exploration and big questions like, are we alone in the universe? And he brought sort of the passion and excitement of space exploration to the public and was very famous and noteworthy for doing that. And he did it with great eloquence and even poetry. So he was quite a remarkable man. And again, he wrote the book Contact that became the movie. Lou Platt was the former chairman of Hewlett Packard back when that was a real computer company in the early days of Silicon Valley. David Newman is at MIT in Massachusetts. She was the deputy administrator for NASA during the Obama administration and was has been the head of the famous Media Lab at MIT since that time. John Andrea on our board is the head of artificial intelligence at Apple. And Avery Wang, for those of you who like music and may have an app on your phone called Shazam, which allows you to identify music you're listening to, that's Avery's work. And Avery is now a fellow also at Apple. Minnie Wadhwa has most recently been the director of Earth and Planetary Science at Arizona State University, but she's now gone on to head up research at the famous Scripps Institute in San Diego. And then Brother Guy Consolmagno is actually the Vatican astronomer. So he reports directly to the Pope and is on our science advisory board together with Minnie. And he is a MIT PhD astrophysicist, but also a Jesuit priest and a remarkable man, and is a very interesting combination of science and spirituality. And then David Grinspoon is a well-known author and scientist in the field of astrobiology, which is the study of life in the universe. So lots of interesting characters, both past and present, in the history of the Institute. So there's three basic ways to look for life in the universe, and those are in situ instruments, which means in situ means in place, where you send instrumentation to a location of interest. And then there's remote sensing, which is where you have the ability to sense objects or phenomena of interest that might suggest the presence of life. And you can do this from a distance, although there are limits. And then there's also SETI observations using primarily radio telescopes, but also optical telescopes to look for so-called technosignatures, or signs of engineered phenomena or technologies from beyond our solar system that would serve as a proxy for life and intelligence. So those are the three ways that we can look for life or signs of life beyond Earth. But before we get into a little more detail about each of those and how they work, I think it's interesting and helpful to understand the scale that we're talking about. Like, where are we looking and how big is this space? And what is what we call the parameter space of this question, are we alone? So let's start with a little guided tour of our solar system. So in our solar system, as many of you may know, we have 8 planets. We have 5 minor planets. We have over 280 moons and over 3,600 known comets and at least 1 million asteroids that we've identified and characterized and study. So it's quite a large place. And for our largest planets of Saturn and Jupiter, they have just 1/10 the diameter of our sun, and the Earth has 1/100th the diameter of our sun, and 1/10 the diameter of these giant planets. So even though we think of Jupiter and Saturn as being these massive planets, in the context of our sun, they are also very small bodies. But planets are important, as we'll see. But what about the distance and the scale here? So it's interesting to note that a photon of light leaving the sun at the speed of light would take 5.5 hours traveling at the speed of light to reach Pluto. So even though we think about light as being, and electricity as being instantaneous and fast, in the scale of just our solar system, things slow down quite a bit. And if you ever have a sleepless night and you're looking for some way to maybe doze off and get some rest, somebody has done actually an animated YouTube video of a photon traveling through the solar system. It's a 5.5 hour long movie, and most of it is empty space. So it does give you a sense of scale that we're talking about here, of just how big our solar system is, let alone the space beyond. And in fact, if you were to launch a spacecraft from Earth, as we did in the New Horizons mission back in the early 2000s, the travel time for that spacecraft was 9 years traveling at rocket speed to get from the Earth to Pluto. And so this was a science mission. You may remember back in 2015, these beautiful images, close-up photographs and images for the first time in human history of the surface of Pluto. And we learned so much about this tiny little world and how amazing it is, with mountains made of frozen water and other extraordinary phenomena. So that was the New Horizons mission. And I'm going to come back to that in terms of scale in just a few minutes. But again, that mission, which took 10 years to develop, also took another 9 years to get to Pluto. So imagine being the scientist who came up with the idea, let's build a spacecraft and go to Pluto and learn what we can. That was a 20-year undertaking. And that, however, is not uncommon in terms of big space exploration missions. So if we go out one step further, we get to our own galaxy, the Milky Way galaxy. This is obviously not actually the Milky Way galaxy, because we've never been far enough away from our own galaxy to take a picture like this, but this is a similar so-called spiral galaxy, a collection of billions of stars that is in a swirling pattern with kind of extending arms from the center. And the Earth and the Sun, our solar system, is kind of on the edge of one of those spiral arms of the Milky Way galaxy. And it wouldn't even be visible at all at the scale of this image. The little circle in red that you can see on this screen would be hundreds or thousands of times or more larger than our actual solar system. But anyway, this is just to give you a rough idea of scale. And the size of our own galaxy is 100,000 light years. So that same photon that would leave the sun and take 5.5 hours to get to Pluto would take 100,000 years to cross the width of our galaxy. So that's the size of our galaxy, and it contains about 300 plus or minus billion stars. And what we now know, and we'll talk about how we know that, is the potential number of habitable worlds, meaning worlds that could potentially serve as a habitat for life to emerge, is in the tens of billions just in our galaxy alone. So we're going to take another step out from our galaxy and look at a very famous image, which was taken by the James Webb Space Telescope, and it's called the Deep Field image. And it's similar to one that was taken by the Hubble Space Telescope many years ago, in which the operators of the telescope said, let's point the Hubble Space Telescope at the darkest point of sky that we can find, where there doesn't seem to be anything there. And let's leave the shutter open for a while and expose the detectors to the light coming in and see if we can find anything. And what they discovered was lots and lots of galaxies, not stars. So most of the little patterns that you see, except for the very bright spots, all those little smudges and swirls and colored dashes in this image, those are all galaxies. Those are the same things that you saw in the previous slide with the Milky Way galaxy. So each of those has itself hundreds of billions of stars, and presumably by proxy also hundreds of billions of planets and tens of billions of potentially habitable worlds. So it's an extraordinary and almost unimaginable scale to think of how large the universe is and how vast it is in terms of distances and size. And so if we think about the scale of science that we undertake at the Institute, for example, we can start at the nanometer scale and the size of things like amino acids, which are the building blocks for proteins, which are building blocks for life. And we study and evaluate these building blocks of life as part of trying to understand the process by which life emerged. So we operate at the nanometer scale, and then the scale of 10 to the 20 meters when we're talking about the Milky Way galaxy, and 10 to the 25 meters when we're talking about the scale of the universe. So it's 34 orders of magnitude, which again is almost unimaginable in terms of how broad a scale is. But that's the parameter space that I'm referring to in terms of how big is the area that we're looking for and looking at to answer these science questions that identified. It's really quite enormous and almost, again, unimaginable. So now we can go back to these methodologies that we talked about before that I mentioned in terms of, so how do we look for life? So the first way, again, is in situ or in place, and that's where we would send a spacecraft like a rover or a lander to another planet or a moon within our own solar system that would have instruments on board that could understand and evaluate the environment, the surface, maybe even drilling below the surface, understand the composition of the atmosphere, use things like ground penetrating radar, spectrometers, vision systems, camera systems, seismometers to look for active geological activity, X-ray diffraction systems to understand the elements that are on the surface of the planet, gas analysis, drills, probes, and more. So that's a really interesting and very powerful way to look for life, because with actual instruments in place, we can get direct evidence of whether life might or might not exist. And you may have seen stories even very recently about the possible detection of or identification of rocks on the surface of Mars that look to have patterns in them that life might have left behind, because we have similar rocks with similar patterns on Earth made by biology or living organisms that leave evidence of themselves in the mineral record or in the rock record. So it's very interesting. We don't yet have any definitive evidence that there's life on Mars. We do know a lot about Mars now. We know that Mars was at one point in its past a warm, wet world with oceans, liquid oceans and continents. We see the evidence clearly of that on the surface of Mars, and therefore it's very likely that at least a very basic form of life may have emerged early on before Mars lost its atmosphere and became sort of a lethal environment for life on the surface. But there could actually even be living organisms below the surface on Mars, protected from lethal radiation. So it's a very interesting place to go. But in situ methodologies, in terms of looking for life, right now, they're limited to our own solar system. We don't have the technology to send hardware beyond our solar system to some other star or some other solar system. It's too far a distance. And so while this is a very important methodology, we can't use this particular technique beyond our solar system. But we have lots of interesting candidates in our solar system, including the moons of Jupiter and Saturn, Europa and Enceladus, and also the moon Titan. All three of these are potentially interesting worlds where some basic form or even complex forms of life may have emerged and may still exist. So the next way to look for life is remote sensing. And remote sensing just means, you're not in direct contact. You're looking at something from a distance, from, for example, a flyby mission, an orbiting spacecraft, or a ground or space-based telescope. And a classic example of this is the James Webb Space Telescope that's pictured in this image here. And you'll note that the mirrors on James Webb are not silver like they are in most telescopes or in our bathrooms at home. They are gold. And they're gold because they're optimized to reflect light in the infrared and near infrared. And so when James Webb takes a photograph of the stars and planets or other phenomena, these are color corrected to compensate for the gold mirrors. But the gold mirrors, since they're optimized for the infrared, allow the James Webb to do something in addition to looking back at the very origins of our universe. This telescope can also look at the thin layer of atmospheres on planets around other stars outside of our own solar system, so-called exoplanets. And it can determine the composition of those atmospheres. Do they have oxygen, nitrogen, methane, carbon dioxide, and so forth? And so with the ability to understand the composition of an atmosphere, it's possible to determine if that atmosphere's composition could only be explained by the presence of life on the surface. Is there either a unique compound in the atmosphere or just the recipe, if you will, the composition of that atmosphere that would suggest the presence of life on the surface below? So these are so-called biosignatures. They are not definitive because you can't necessarily prove without further investigation that there might be life, but it's very interesting to note that we can at least get the signature or the possibility or the prospect of life on the surface of a planet just by understanding what's in its atmosphere. Another interesting thing is there are so-called technosignatures that could be in atmospheres, and these would be chemical compounds that, for example, only industry or technology produce. Some of the compounds that come out of smokestacks, for example, in our factories or processing plants on Earth are synthetic compounds that nature doesn't produce, that are only produced by industry or technology. And if we found those molecules in exoplanet atmospheres, it would be reasonable to assume that they are also sourced by technologies on those worlds. So they would be technosignatures, and they would actually be a little more definitive than the so-called biosignatures. But in terms of the scale, like how far away can James Webb look at a planet's atmosphere and do this kind of analysis? And the answer is up to maybe 1,000 or a few hundred light years rather for small rocky planets like Earth. But for bigger planets, which are easier to see and characterize, it can be up to 1,000 light years or more. And within 1,000 light years of Earth, there's hundreds and hundreds of planets. So there's lots of different worlds that can be interrogated or investigated with the James Webb Space Telescope. But remember, going back to our galaxy scale, that our own galaxy, just one of hundreds of billions, is 100,000 light years across. So 1,000 light years is only just 1% of the distance of our own galaxy. So it's also, a pretty close neighborhood that we can investigate through remote sensing. And then the third way, again mentioned previously, is SETI. And SETI is an acronym. It stands for the Search for Extraterrestrial Intelligence. It's actually not quite accurate because we're not looking for intelligence directly. We're looking for technologies that would suggest intelligent species develop those technologies. So it's really a search for extraterrestrial technology, which would serve as a proxy for the presence of life and intelligence. And we do this using ground-based radio telescopes, primarily all over the world, and optical telescopes. And these are designed to look for signals or phenomena that are different and distinct from what nature produces. Nature also produces things in both the radio spectrum as well as the visible spectrum, and X-rays, and across the board. But engineered phenomena are separate and distinct from what nature produces. And these are what we look for with our radio and optical telescopes. And so radio signals or laser transmissions coming from a distant world would be examples of what we call technosignatures. And in this case, detection would serve not only as a proxy for life and intelligence, but it would be definitive. It would be like, okay, there's no question in this case that we've got direct hard evidence of an advanced technological species, because this is such a firm and final characterization. And the scale or the distance that SETI technologies can interrogate is our entire galaxy, and potentially, depending on the strength or power or energy of the event that we might detect, it could even be something from another galaxy. So SETI takes the scale from our solar system for in situ and 1,000 light years for remote sensing, and extends it all the way to the edges of our galaxy or beyond in the case of SETI technologies. So that's how we do it. Those are the primary methods that we do. And let's talk about like a framework that would say, well, what are the questions that we're trying to address when we pursue this science? And so this brings us back to Frank Drake. And Frank Drake, again, was a radio astronomer. He was at Cornell University, and also a colleague with Carl Sagan and with Jill Tarter. And back in 1960, Frank conducted the very first SETI experiment using a radio telescope in Green Bank, West Virginia, to look for evidence of advanced technologies beyond Earth. And in fact, when he did his experiment, he initially thought, oh, I have found something, because he did find interesting radio signals, but it turned out upon closer inspection that these were either passing aircraft or satellite or something along those lines. It was local, it wasn't distant. And this is one of the big challenges we have, particularly in radio astronomy, is we have a very noisy environment with aircraft and spacecraft and garage door openers, cell phones, microwave ovens, all of these things which interfere with doing radio astronomy. So there's a lot of noise to filter through when we're trying to find that weak signal from deep beyond. But Frank was asked in 1961 by the National Academies of Science in the United States to gather with some colleagues, scholars, and scientists to talk about whether searching for extraterrestrial intelligence was a reasonable scientific thing to do. And so he and Carl Sagan and a couple of astronomers and radio technologists and engineers and other scholars got together again in West Virginia at the Green Bank Observatory to ponder this question: does SETI make sense to do? And Frank's job was to put together the agenda for that meeting. And so he put together a series of questions that he thought would be the kinds of questions we need to ask. And they were, what is the birth rate of stars? What is their life cycle? And how many stars have planets? And if there are planets, how many are potentially habitable Earth-like planets? Not too big, not too small, the right distance from their host star, in the so-called habitable zone or Goldilocks zone, to potentially support liquid water and the conditions necessary for what we understand to be right for the development and emergence of life. And how many habitable planets, if there are any, go on to develop life? And if life happens, in how many cases does evolution have enough time to generate complex and intelligent life, which on our own planet has existed for hundreds of millions of years? And if intelligence emerges, how often does a technological civilization arise? Well, humans have been around modern humans for a couple of 100,000 years, but only in the last 100 years, which is like the blink of an eye in a human lifetime, has a technological civilization existed. and by that, a civilization that, for example, is making radio waves and can detect radio waves and essentially make their presence known beyond the confines of their planets, and also look for similar technology. So humans have only been technological for a very, very short period of time, about 100 years. But he wanted to know how often that happens. And if that happens, how long might a technological civilization remain detectable before they either cease to exist or perhaps evolve into something using other methods or other technologies beyond our comprehension or our ability to observe. So these were the questions that Frank thought if we could answer those questions, we could come up with an estimation for the potential number of habitable, of rather intelligent civilizations that might exist in our galaxy. And he realized that he could express all these questions in a formula. And he then came up with this formula, which is the number of technological civilizations in our galaxy is going to be a product of the birth rate of stars, the number of stars with planets, how many of those planets are habitable, in how many cases does life, intelligence, and technology emerge, and then how long do those civilizations remain detectable. So that became known as the Drake equation, which is considered by many to be the second most famous equation or formula in science, second to E equals mc squared. And while it looks complex, it's really just a straightforward, you multiply each of these things together as a series of probabilities to come up with this estimate. It was never intended to come up with a precise answer, but rather it provides a framework for understanding how we might estimate this number and what things to look for. So as it happens, most of the scientists at the SETI Institute, if not all of them, would identify the kind of science they're doing with one or more of these variables. Some of them are astronomers who study stars, and some of them are astronomers who study planets, and some of them are astrobiologists who study things like habitability and life, and others are studying, neurological functions, intelligence, and technology, and so forth. So it turns out that while this wasn't the original purpose, this Drake equation is indeed a roadmap for astrobiology and SETI endeavors. So what we do at the Institute, we do research across all of the natural sciences. We have over 100 PhDs, and they represent everything from chemistry, physics, biology, astronomy, astrophysics, geology, geophysics, planetary science, and more, because you need all of those different disciplines to interrogate such a profound question as life beyond Earth. We support NASA science missions. These are primarily the unmanned or unpersoned spacecraft that NASA launches into our own orbit or deep into the solar system to study other planets and moons. We do field expeditions all over the world, as pictured here in the Atacama Desert and the frozen lakes of Antarctica. We do laboratory research. We do optical astronomy using ground and space-based telescopes. We do radio astronomy with ground-based radio telescopes and do astrophysics and theoretical work. And we also develop technologies and instrumentation. For example, on the Curiosity rover on Mars, there's an instrument called the ChemMin system. This stands for chemicals and minerals. And it's an X-ray diffraction system that tells scientists what the elements are that are on the surface of Mars. And that was developed by the SETI Institute together with NASA Ames Research Center. And through all of these efforts, what we're trying to understand is the structure of the universe. We're trying to understand planetary environments and what habitability means and where else we might find it. We're trying to understand the nature and the origins of life, how life even emerged, and then ultimately the evolution of intelligence and technology. So those are the things we're trying to do. And, a typical day at the office is supporting missions like Cassini, which is now over, or TESS, which is the Transiting Exoplanet Survey Satellite, which is an ongoing mission, or the Perseverance rover, or New Horizons, pictured on the right, that went to Pluto. We're using ground-based radio telescopes, doing field expeditions in Atacama, Antarctica, the Andes, and so forth. So these are the kinds of things that go on day in and day out at the Institute. One interesting side note that I forgot to go back to when we were talking about the scale. So that spacecraft on the upper right, New Horizons, happens to be the fastest object ever made by humans, traveling in a straight line. We've made spacecraft that are zipping around the sun and getting gravitational assistance and going much faster. But in terms of something traveling in a straight line, other than in a particle accelerator, this is the fastest object made by humans, faster than bullets or guns or missiles or rockets. It's traveling at 56,000 kilometers per hour. But just to give you an appreciation of the scale, if we sent that spacecraft to our closest neighbor star, which is Alpha Centauri, that's our next door neighbor in our galaxy, the Milky Way, Alpha Centauri is 4.2 light years away. And compared to 100,000 light years of our galaxy, that sounds like nothing. But that 4.2 light years would take New Horizons 80,000 years, 80,000 years to cross that distance. So the scale, again, is really hard for us to comprehend, but that helps give you a sense of why right now our in situ technologies, for example, in terms of looking for life, are confined to our own solar system, because we can't get to other solar systems with the current technology that we have. In terms of SETI programs at the Institute, we have our own Allen telescope array, which is a 42 dish array of 6-meter telescopes up in the hills of Northern California, far away from civilization. I mentioned the problem of radio interference and noise. So when you build radio telescopes, you want to put them far away in isolated areas, and as we have done with the Allen telescope array. We also use the Very Large Array in New Mexico. This is a series of 27 dishes, each of which is 25 meters across. So these are great big telescopes in New Mexico. And we are doing a survey in conjunction with the standard astronomy that telescope does. And we're looking at the sky 24 hours a day, 7 days a week on the Very Large Array. And in both cases, just for those of you who are into data and computers and things of that nature, we're generating data at a rate of 3 terabytes per second with these instruments, and we're processing that data in real time thanks to NVIDIA and GPU technology. So the amount of information we're collecting and processing is extraordinary in these systems. And we also have a laser SETI program, which is designed to look for laser technology, which could be coming from space. It could be being used for communication or propulsion. We have a laser up the street from our institute in California at the Lawrence Livermore Lab that is used for nuclear fusion experiments. It's the most powerful laser in the world. And if you took the output of that laser and bounced it off of one of our ground telescopes here on Earth and sent it off into space, it would be 10,000 times brighter than the sun at its own particular wavelength and for very short bursts of time. So it's the kind of thing that would be very easy to spot even from great distances, and would be very distinct from the light coming from other stars. So that's the laser SETI program. So those are the kinds of SETI activities we do in addition to the other sorts of science. And as far as our field expedition work is concerned, again, it's between optical and radio telescope partnerships we have around the world. We do research in the field across almost all the continents. And some of these environments we actually call analog environments, because there might be something similar to conditions elsewhere, like in our solar system. If we go to the 20,000-foot peak of a volcano in the Chilean Altiplano, that top of that volcano is very similar to the conditions on Mars in its first billion years in terms of atmospheric pressure and composition and temperature and so forth. So we can go to places that have things similar to other worlds of interest and learn about how to look for life, what technologies to use, what methodologies to use, and what signs life leaves behind that can inform us of how to look for it elsewhere. And in terms of this astrobiology as a fundamental study of life itself, not just technology, the 3 primary questions are: how does life begin and evolve? And does life exist elsewhere in the universe? and what is the future of technological life? So these are the big questions in astrobiology as a subset of SETI. And so we want to, through our astrobiology, again, understand origins and evolution and distribution of life, as well as the future and potential of life in the universe. So this really is based on fundamental and basic concepts of life and habitability, habitable environments, and all of these studies or inquiries help us recognize biospheres or potential environments that might be quite different from our own, but still harbor life that we can identify. And I would say that what's, for me, particularly interesting about the work at the Institute and how we do it and what we do, it really is about connecting the dots. That in science on Earth, we study chemistry and physics and biology. We study astronomy and geology and climate science and planetary science. But remember that these are all human inventions, that these are all a way for us to categorize different phenomena and study them individually, sort of take things apart, take a deep dive and understand them. But nature isn't divided into these compartments. Nature is all of these things working together in a very complex system all the time. So it's really about connecting the dots. So one of the things that we do at the Institute, one of the reasons that we are so-called multidisciplinary, is that we want to understand the relationship between all of these things and how they work together to become a system, a complex system that resulted in life emerging on Earth. So that's a key element and characteristic of the Institute, is what we call connecting the dots. Now let's shift to this notion of planets and habitability and life. And I want to show you this picture because if you look at this picture, you'll see the band of the Milky Way. This is an actual photograph of a night sky from a clear, dark area on a moonless night. And you can see the band of the Milky Way. And of course, what you see in this picture is stars, millions or tens of thousands of stars in this image alone. But what I want to tell you is these are not just stars. They are, in fact, solar system. That statistically, we now know that every star in the sky has one or more planets around it, not just an isolated star. So a nice fun fact for you to tell your friends or your romantic interest on a beautiful starry night is look up in the sky and realize that what you see are not just stars, but you're seeing entire solar systems. And that's kind of a fun fact, but it's relatively new information. We're living in a time that I refer to as a new Copernican revolution. Copernicus, as many of you may know or remember, is the one who taught us that the Earth goes around the sun and not the other way around, which is what humans believed for many hundreds or thousands of years prior to Copernicus proving it's a different setup. So that was a revolution in human knowledge and understanding of our place in the cosmos. And we're in another profound area of new knowledge along those same lines. And that's primarily due to these three gentlemen, Didier Queloz, Michel Mayor, and Bill Baruch, and also an instrument called the Kepler Space Telescope. Didier and Michel Mayor shared the Nobel Prize in Physics in 2019 for the first discovery of exosolar planets, so-called exoplanets. Exoplanets is a word that wasn't even in our vocabulary when I was a kid, but now I think most people, and certainly most young people in school, will have heard of exoplanets. And they discovered these in 1995, big planets, and for that they won the Nobel Prize. But then Bill Baruch came along and said, well, okay, we found a few big planets, but they're not probably very hospitable or habitable for life. Can we find Earth-like planets, smaller rocky planets? And so he designed a space telescope where he told NASA, I think we can detect Earth-like planets around sun-like stars. And it took him 5 times to convince NASA that this could be done. They didn't think that we had the technology, but he proved them wrong. And so he designed the Kepler Space Telescope, and the way it worked is it was looking at stars, and if those stars happen to have planets around them, and if those planets happen to have an orbit in our line of sight, then theoretically, the amount of light that we could detect from those stars would dim ever so slightly every time the planet passed in front of the star, a so-called transit, like a little eclipse, basically. The telescope did not see stars looking like this big orange globe. It still just saw tiny dots in the sky. And in fact, it was looking at over 200,000 stars at the same time. But it was staring at these stars for 3 years and recording these dimming events. And to give you an idea, this is a very exaggerated dip in the graph you see on the chart here. An Earth-like planet around a sun-like star would only dim the light of that star by 1 part in 10,000. So a tiny, tiny amount, which is why NASA thought it'll never work. But he developed the instrumentation that was sensitive enough, and it was successful. And here's what Kepler discovered. This was what the knowledge of planets around other stars looked like in the early 2000s. We had found lots of big Neptune and Jupiter-like planets through a couple of different technologies, but we didn't know anything about Earth-like planets. And then here's what Kepler saw. Thousands of planets, about the size of Earth, some smaller, some bigger, sort of the sweet spot was somewhere between an Earth-sized planet and a Neptune-sized planet. And this was revolutionary. And not only could Kepler discover these planets, it could also tell, based on the distance of the planet from the star and the energy flux from the star, whether these planets were in the so-called habitable zone of their star. And what it determined was around 30% of these planets were rocky, Earth-like planets in the right distance from their star to potentially be habitable for life. And since the probability of an orbit being just in our line of sight is less than 1%, the math suggested that, okay, what we now know is planets are ubiquitous, that every star in the sky, statistically speaking, is a planet. And that is profound new information and really has transformed our sense of our place in the universe. So what Kepler taught us is that every star in the sky has one or more planets. The majority of planets fall between Mars and Neptune in size, like Earth, that about 20 to 30% of all planets are rocky, Earth-like, habitable zone worlds. And that means between 10 and 60 or more billion potential Earth-like environments just in the Milky Way galaxy, just in our galaxy. So that's an extraordinary discovery. And that's probably the most profound progress. When we talk about, where does it stand? What do we now know? Well, we now know that there are candidate worlds everywhere. And that, of course, certainly increases the probability and the likelihood that life has emerged, and potentially technical life as well. So that brings us back to the Drake equation, and how much do we know now? Well, the one thing we knew, even at the time this was put together back in the 1960s, we knew at that time the birth rate of stars. We didn't know anything about the rest of the variables in this formula. But we now know, thanks to the Kepler mission, that every star in the sky has planets, and about 30% of those are Earth-like planets in the so-called habitable zone of their star. So that's now factual information, and again, it's transformative and profound in its nature. But we still don't know in how many cases life has emerged, or intelligence, or technology, and therefore, we don't know much else about the duration of technological civilizations, although we can see what's happening to our own technological civilization and the challenges we face. So that's that's one piece of evidence. But these are still questions. We jokingly refer to these as job security, because they remain things that we have to investigate. But the fact of the matter is, when you're doing science, you're doing good science when every time you answer a question, as a result of that, you raise 10 new questions. That's what science does. And so we'll never run out of questions to pursue, even as we fill in these blanks or answer these questions. So that's the nice thing about science. So ultimately, all of this is really about the future of life on Earth and beyond. So life starts here on Earth. What we can learn about the so-called coevolution of life and environment on alien worlds helps us better understand life and habitability on our own planet. And it also helps us identify habitability thresholds that we should not cross. in terms of things like climate change and environmental protection. So habitability and habitable environments that are sustainable for life and the evolution of intelligence can tell us a lot about our own situation here on Earth. And astrobiology teaches us to develop a responsible approach to our own environment as a civilization and as an advanced species on this planet. And hopefully it prepares us to become an interplanetary species that we're around long enough and survive long enough to develop those technologies that allow us to become interplanetary. And all of this also extends beyond our own relationship with our own planet. It really gives us an understanding of the future of life as a process in a universe that's constantly changing. That is also for sure. The universe is dynamic. It's not static. It's constantly changing. And ultimately, this is really about what it means to be human. So it's about curiosity. Curiosity is perhaps the one trait of our species that we all share in common. It doesn't matter what background we come from, our ethnicity, our country of origin, our language. We're all fundamentally curious as a species. And the search for life beyond Earth engages that human curiosity. And curiosity unites us as human beings and explorers. And it's not just the curiosity of the what, which animals have, like what was that noise? Or what, is that a food source? Or is that a mating partner? But really the how and the why. How is it this way? Why is it this way? Why do we even exist? And how did we get here? And are we alone? So these fundamental questions really exercise our curiosity. And curiosity is, in fact, the motherhood of invention, not just necessity, which is a saying here in the US, but curiosity is the mother of invention and understanding. And also the sense of wonder. So SETI and astrobiology trigger this sense of wonder and awe. So what we do brings us face to face with just how big and vast our universe is. It's unfathomable scale, and it actually, compels us or dares us to ask big, profound questions in science, like, are we alone? And does life exist elsewhere? And what about intelligent life? So pursuing these questions inspires us to develop some of the most advanced technologies ever imagined. It compels us to explore and discover, and that really ultimately brings us face to face with ourselves. In other words, what it means to be human. So it is about human nature. We're social beings. We don't want to be alone. We don't want to think that this is the only place in this vast universe where life has emerged. So even our fascination with things like UFOs tells us more about human nature than it does about the prospects of aliens flying around in our airspace. We want to believe that we are not alone, and most likely we're not, but we don't yet know. The quest continues and carries on. So with that, I'd like to share with you what we call the trailer for the movie we make in real life every day, and you may recognize the voice of the narrator.
Finding life beyond Earth is no longer a dream. It's a discovery that will likely be made during our lifetime, and it will change everything. We've been here for more than 36 years, at the forefront of a quest that many consider science fiction.
Mars is the closest planet where we might find the possibilities of alien life.
We are home to over 100 neuroscientists.
It just takes your breath away.
Our purpose is singular.
Best to understand what you have in your own backyard as you're looking up into the cosmos.
To understand the origins and prevalence of life in the universe.
What we are doing is to try to understand, are we alone in the solar system?
Why do we pursue our mission? Because the discovery of life beyond Earth will lay the framework for humanity's next steps. Stars.
We are trying to understand why we even exist.
We are the SETI Institute.
Okay, so I always put this at the end because I would not want to follow Morgan Freeman in any act. So, but I think he puts it pretty eloquently. And with that, I do want to introduce you to our website, SETI.org. So if you are curious, you'd like to learn more about what we do or how we do it, or you want to get involved, that's the place to go. We'd love to get to know you and have you get to know us. So do come and visit. And with that, I'm ending almost precisely on time, which is very unusual for me. But I hope you found this interesting. And I think we're prepared now to take questions. And with that, I guess I will stop sharing my screen, which I do here. And hopefully that worked. Okay.
So thank you very much. Thank you very much, Bill, for your beautiful presentation. And what we can see on our screen, we have a surprise today. Sabine Hine is with us. Sabine, very welcome here. You know, this is your creator. You conducted our webinar series for 3 years and more, maybe, almost 4 years. And let me say, our almost 100 webinars that we have collected from the beginning in 2021 are fruit of your work. So I'm very happy to see you here. I know you will have a lot of questions for Bill that, by the way, was invited by you to hold a lecture with us. And yeah, I know that we have some questions also from the audience, and maybe Maria can manage this question and transmit these questions to Bill for an answer. So I just want to thank you very much, Bill, for your beautiful lecture. And I have to also say that we already commenced preparation of our fourth World Congress that will take place next year, end of June. And we are already making preliminary webinars for the Congress. So for in the next months, we will see many speakers talking about the key title of our Congress is quality of life on Earth and beyond. And so many things to discuss about this point, and for sure we will go ahead. Sabine, maybe you want to say something? Be the first to make a question.
I want to give first the floor. Hello, Bill. I'm really
Hello,
happy
Sabine.
to see you. I'm happy to see you all. I only want to make a remark. I hope you can see this very well. This regarding the dots, I made this for my husband one time ago regarding that the Milky Way is settled. So I hope one day we will have all the dots, all the planets connected from the Milky Way. And yeah, I would like to give Maria the floor because she is the host today and I'm only a guest. So Maria, you may take the questions from the chat and then I can go on.
Hello, Sabine. Nice to see you. Thank you. Actually, we have one question from the chat on YouTube. I also copy-pasted it here in the chat if you want to see it. So what do you think of the possibility that 3i Atlas was at the location where the WOW transmission came from?
I think it's coincidence, but an interesting coincidence. And of course, there's lots of interesting coincidences. I mean, how interesting, for example, is the coincidence that in our night sky, the moon, which is 250,000 miles away, and the sun, which is 93 million miles away, are exactly the same size. in terms of diameter from our point of view. I mean, this is a coincidence, but it's an extraordinary coincidence. So I think that is also a coincidence. I mean, the WOW signal, we have never been able to repeat or verify. At the SETI Institute, we actually did another investigation of that quadrant of the sky in parallel with the Green Bank Observatory in Virginia. We didn't see any evidence, and we have, of course, far more sensitive telescopes and instruments than they had at Ohio State, where that initial discovery was made. It was certainly interesting, and it got people's attention, as well it should. But it was most likely, local interference from a spacecraft or, aircraft that was going overhead at the time. So it's, but again, it speaks to how fascinated people are with this subject, and how excited they get when even the most remote possibility suggests that, we have. So anyway, the Atlas object or comet is interesting, but doesn't, there's nothing to suggest that there's anything alien in its nature.
Okay, thank you for the answer. And no more questions actually from the chat. Just people thanking you from Cape Town, from Rocky Mountains, northern Colorado. Anyway, people from everywhere. So yeah.
No questions. I'm amazed. That's good. Maybe I answered all the
question.
questions. I don't know.
You were clear.
Yeah, maybe that's it.
Yes.
Yeah. So maybe some final points, or Sabine, would you like to say something also?
Yeah.
Yes, please.
I also would like to thank you very much for this interesting lecture, and that you followed my invitation. It's nice to see you, by the way. And I wanted to ask if you have some collaboration with ALMA Observatory in Chile, and if you have some time there, and
yeah. So the ALMA Observatory is a radio telescope array in Chile, operated by the European consortium, and the ALMA array is not doing SETI radio astronomy per se at this point in time. It's tied up doing more fun, basic so-called astrophysics using radio telescopes. So we have partnerships with, and particularly in relationship with the Breakthrough Listen initiative, which is also a SETI program, with the Parkes Radio Telescope in Australia, the Square Kilometre Array in South Africa, and the low frequency version of that also being built in Australia, with the Sardinia Radio Telescope in Italy, the Green Bank Radio Telescope in West Virginia, and the Jodrell Bank Telescope in the UK. So these are the primary other telescopes that are doing SETI research specifically. We know and work with in terms of cosmological radio astronomy, the folks at ALMA, but they don't do SETI research at this time.
Thank you. And another question is, what if we find the aliens? I know there's a procedure. Maybe you can say something for our audience about this. And my question is also, what do you think personally would happen? Also, first the official part, and then what you think personally.
Sure. Well, that's a great question. We get that question a lot. And I would say that the answer depends very much on the nature of the discovery. So, for example, if we get a biosignature, from a planet or a moon in our own solar system, that is unlikely going to be, there's not likely any technological or advanced life in our own solar system, but there could be not just microbial life, but below the icy surface of Europa or Enceladus, there could be complex life like we have in the ocean, the deep ocean thermal vents here on Earth. And that would be fascinating. In particular, if we find evidence of life from, deep in our solar system, not necessarily Mars, because Mars and Earth exchange materials over time. But if we found life on Europa or Enceladus, it would clearly have its own unique, what we call biogenesis. In other words, its origins would have nothing to do with the origin of life on Earth. It would be its own origin story. And that would be profound because it would also say to us, okay, life is probably an emergent process, which is something I personally believe, that it is a natural byproduct of the existence of planets and moons, provided those planets and moons are, in a potentially habitable state. And they don't even have to be in the habitable zone. Like Enceladus and Europa are far away from the habitable zone of our sun, but because they have their own internal heat source, they could potentially be life supporting bodies. So, I think that life is likely, since it's, the building blocks of life are the most abundant common elements in the universe, and they're everywhere. Hydrogen, oxygen, nitrogen, carbon, et cetera. These are the lowest and most abundant elements on the periodic table. So life got formed on these basic building blocks. And since they're everywhere, the likelihood is that there are many other places where they have come together for life to emerge. So if we make that discovery, we'll of course announce that to the world. We would announce what we discovered and what we can ascertain or conclude from that discovery. We've already had several examples of possible discoveries in our own solar system. We had the phosphine potentially discovered in the Venetian atmosphere. We have actually the discovery of dimethyl sulfide, or supposed discovery in an exoplanet. And dimethyl sulfide is a compound which we believe only life can produce. And I think there's even a second dimethyl sulfide discovery that looks more promising than the first. And then we've discovered, this potential evidence of life, past life on Mars in the mineral record. So, and all of these have generated a lot of press, a lot of excitement, a lot of speculation. So I think that's a good hint of what would happen if we got a technosignature or evidence of, intelligent technological life.
Yes.
I think the world would go a little nuts, frankly speaking. It would be the biggest news of the day for sure. It would at least for a little while, it would overshadow all other news on the planet. It might be a good thing in some cases, but this would be a profound discovery. What would we do? So the first thing that we do as far as a protocol goes, if we make a discovery like with a radio telescope, first thing we would do is get another radio telescope observatory to look at the same place in the sky and see if they can verify what we saw. Because if we give them the coordinates and a faraway telescope looks at those coordinates and doesn't see anything, that probably means that the object wasn't that far away. Whatever generated the signal it must be closer by. If that faraway telescope does make the observation and confirms it, then we have an announcement to make. We would basically what we would do is hold a press conference and we would tell the world what it is we observed. We wouldn't really likely be able to make any conclusions about the nature of the civilization that sent the signal, whether it was intentional or just an accidental observation, whether it contains information or is just, a pulse of some sort that is part of their technology. We could only just share whatever it is we've observed and whatever it is we can characterize about the phenomena. We could tell how far away it came from, and we could explain the nature of it. And we would probably stop there. We would not make wild speculations beyond what we could observe. We would almost certainly be encouraging the further investigation of this particular location or this particular world so that we could learn more. But also if a signal is detected from relatively close by, like within 10 or 20 or 30 or even 50 light years, well, that would be extraordinary because it would mean that potentially we could have a conversation. In other words, we could send something back and it would take 10 or 20 or 50 years to get there. But, within human generations, a conversation could happen. Whereas if it's 1,000 light years or 10,000 or 50,000 light years away, we don't even know if the civilization that transmitted that phenomena or emitted that signal even exists anymore, because it would have been so long ago that it left that particular place. So I think, we are starting to spend more time with social scientists and philosophers and anthropologists and others to start thinking about, as this gets more realistic and more likely a discovery, we should start thinking seriously about the effect on humanity, and how are people going to respond? What is it going to mean to religions and to technology and to governments and to people in general? Are they going to be afraid or hopeful? I'd like to think that it would be a very uniting time for humanity, that we would begin to see that, my gosh, we're all just one species on this one little tiny island of a planet, and we should start getting along with each other and operate as one species on an island, instead of, fighting over the resources of this island, and take better care of the island. So I would like to think that good things would emerge from this discovery, but like everything, there will be all kinds of noise in the media. There will be conspiracy theories, and there will be wild speculations, and there will be inaccurate statements being made by individuals, and so forth. Our job will try to be to maintain the disciplines of science and scientific rigor, and keep information under control as best we can.
Maria, I think there's another question in the chat.
Yeah, actually, we have one more question from the chat. So, how should we critically evaluate the recent announcement from NASA that biomolecular signature of life has been found on Mars?
Yes, I would say with caution. It's very interesting, but it's not the first time that there's been some evidence, photographic or otherwise, from rovers on Mars or other instruments, where we say, yeah, gee, this looks like it could be, a sign of life. And I urge the scientific community and the media to be cautious in making speculations, because what we don't want to happen is to have a lot of announcements get made over time, and every time they get made, a few weeks or a few months later, we're retracting them or pulling back or saying, well, it wasn't really. Because then when we have a real announcement to make, the world will be like, yeah, every time you guys tell us something interesting, a few weeks later you're retracting it. And I think that's a very dangerous situation to get into. So for that reason, we always say, and this was evoked by the famous mathematician Laplace some centuries ago, and then reiterated by Carl Sagan, extraordinary claims require extraordinary evidence. So if you're going to make a claim that we found life elsewhere, make sure the evidence is rock solid and very compelling. And otherwise, what you can talk about is the possibility, like we've found something that suggests the possibility of life on Mars, or looks very interesting, but don't come out and say we have found evidence, unless it's 100% certain, because that does science a disservice. The discovery on Mars is very interesting. There are patterns left in these rocks and minerals which look exactly like the patterns left behind by microbes on Earth, and so it's like, yeah, this pattern is the same as the patterns we see here when life has left its mark, in the fossil record or in the mineral record, and that is interesting. But can we say for sure that there aren't other natural processes that might have left these same patterns behind? We don't know yet. So I think it's really interesting. It's really exciting, but we should be cautious and not jump to conclusions. And neither people at NASA nor in the press should be saying, hey, this is it. This is the discovery we've all been waiting for, until we know more. But it is very exciting for sure.
Thank you for your answer. I hope the person who asked the question got also the answer and still with us. I don't know if someone wants to add anything. Sabine, Adriano, maybe.
Yes, I have a couple of questions too. I start from the lighter of the two questions, and it's still about Atlas 31. You know that we are reading many things on the web and many speculations about the strange behavior of this comet coming from outside our solar system. They wrote that it is changing direction, is changing velocity, and a lot of strange behaviors. So, can you tell us which are the really strange anomalies of this object with respect to the inventions that, of course, the web is full of this kind of things. And if you think that there is a really possibility that this can be somehow an artificial object, maybe inhabited by someone coming from outside, or this is something we have to forget because it's out of any possibility.
Sure. So it is interesting. I will say that I have not studied in detail all the different observed phenomena of this object that might suggest it's technological. So I can't speak knowledgeably about its change in vector of direction or speed because I don't know enough about the specifics to comment on that. What I can say is that nature has an interesting ways of surprising us that we often make discoveries of things that we thought, well, this is impossible. It's impossible for nature to do this, and yet it does. I mean, when we first discovered exoplanets, we found massive Jupiter-sized planets zipping around their host star in 4 days. I mean, it's hard to imagine. Our Jupiter takes 30 years to go around the sun. So it's hard to imagine something so big moving so fast around its host star. And yet we found this. And it was stunning and surprising. So I don't think that just because we observe something to be moving in a way that we don't expect means that it must be artificial. At the same time, we shouldn't rule out the possibility that it is artificial. These things should remain in the domain of the unknown until they are known. And when they are unknown, we can make observations, and those observations may suggest certain possibilities, and we can express those possibilities. It's just important that we express them as possibilities and not definitive answers. We had the same thing with this object that was called Oumuamua, which moved through our solar system in a manner that one person in particular, a famous astronomer from Harvard named Avi Loeb, concluded meant that this was a spacecraft. And that object was never more than 1 pixel in our sensors. We could tell a lot from the way that pixel changed over time, but it was impossible to determine and conclude that this was a spacecraft or some non-natural thing. And I think the same is true here with Atlas, that it might be doing some interesting things in terms of the way it seems to be moving, but they may be natural phenomena, not necessarily mechanical or artificial. At the same time, if this craft is artificial, it is a technological craft, then of course it raises some interesting questions. Where did it come from? Well, it certainly came from outside of our solar system. Now, bear in mind what I said before about how long it would take our fastest spacecraft to travel just to the next nearest star. So the closest place that this object could have come from would be Alpha Centauri. And our technology would take 80,000 years to get there. So if there is a civilization that has put a spacecraft in our airspace, in our solar system, they have technology probably that we can't yet even imagine. At the same time, the likelihood would also be that if this were a spacecraft, it would almost certainly be a probe, meaning there's no biology on board, that it's just a probe, it's a robot. Like our most distant spacecraft, the most distant objects that we've sent from Earth are all probes. They're machines. They have no biology on board, at least not on purpose. The farthest humans have been is the moon, which is not even, it's 250,000 miles away. Pluto's billions of miles away, and that's in our own solar system. So humans haven't gotten very far. Biology is very difficult to send over great distances, and things like microgravity and the radiation of space are really hard on organic matter of any kind. So, a spacecraft would be more likely to have either, no sort of intelligence on board other than sensors and instruments, or robotic intelligence on board, but very, very unlikely to have organic intelligence on board. Not impossible, but very challenging. Now, again, a very advanced civilization, maybe they've figured out how to fold space and time, or to travel through wormholes, or these other things which our theorists speculate about, but for which we can't imagine the technology. I'd also like to think that if something like this were a probe, that it probably knows about Earth, or the civilization that sent it here, and one would expect it to come a little closer and maybe take a closer look at us, rather than just to zip in and out of our solar system without stopping. So I don't know. Lots of questions are raised and possibilities. We have to be careful not to dismiss these ideas, but at the same time, we also have to be careful not to accept them as facts when they're not.
Yeah, however, you don't exclude that it could be an artifact, not simply a natural.
No, I do not exclude that. I don't accept it as a fact, but I also don't exclude it as a possibility. It is a possibility.
Good, thank you. So I said I had another question. This is more heavy. At a certain point of your presentation, you named some thresholds that should not be crossed, about the condition of life on our planet, that we should not go to not exceed what I call the pressure on our habitat, and considering that we are 8 billion and 300,000 and 300 million so far, and we are going to be 9 billion probably in a few years. A little bit later in maybe just one paragraph after, when you say thresholds that should not be crossed, you talk about perhaps starting expanding outside our planet. So I would say that I would change that word. That cannot be perhaps. It is an obligation at this point, because I think we cannot accept any downsizing of our humanity, because all lives are precious, and more lives means more ideas and more possibility of evolution. So we have to keep on growing, and we can only doing that outside of our planet. Otherwise, the pressure on this world will make this magic world inhabitable.
That's true. Yeah, I mean, I think I would agree that it would be nice to be able to continue to grow in numbers, if that means, new ideas and new perspectives. But I also agree that we cannot grow much in numbers, on our own planet. We cannot and should not downsize intentionally, but we may downsize by virtue of our impact on our environment, which may downsize us for us without our having any choice in the matter. And so that's something that we should be concerned about and thinking about and trying to avoid, or trying to manage and mitigate, because we can't continue at the pace we are going to continue warming our planet and to continue to consume resources faster than the planet can restore them or replenish them, or to produce waste and byproduct faster than the planet can absorb them. And all of those things we're doing now. So we have to change our behaviors. And I think our governments have to get far beyond agreeing that we shouldn't, increase temperatures by more than X, Y, or Z amount. This accomplishes nothing. What the governments are not talking about is how to achieve that objective. And they should start talking about what are we going to do together to prevent these temperatures, it makes no difference to stand up and declare that we all agree we shouldn't exceed these temperatures, because if you don't do anything about them, you will exceed these temperatures. We are going to exceed the temperatures of the UN Accords, whether we like it or not, because it's too late to stop. The question is, can we take actions to start slowing that down, and maybe even reversing it? But if all we do is talk about the limits and we don't do anything about it, we're not in good shape.
Yeah, they are spending our money for weapons now to increase.
Well, yes, yeah. That is the problem. That one of the problems with climate change as a phenomena is that it's slow moving, and it's not immediate. And there are always more immediate and pressing threats or issues that we're dealing with that distract us from what is, in fact, a much more important issue than any international conflict. The global climate is the issue of our time, but our political leaders don't see it that way. And until they do, we're kind of in trouble.
Yeah. Okay. So, Maria, do we have other questions maybe from the chat?
No. Oh, I have one question. How accurate is the atmosphere readings by GWSP compared to our current atmosphere readings for Earth-like planets? Can the IR pick up radio waves or tech from exoplanets?
So the infrared information that James Webb gets allows us to do what we call molecular spectroscopy. And molecular spectroscopy is a way we have of detecting both the type of molecules that are in an atmosphere and also their relative concentration. And molecules are, groups of atoms, and these atoms vibrate, they spin, they rotate, but they do all these things at very specific frequencies or wavelengths that happen to be in the infrared. And so what James Webb does is, what happens is the starlight from the host star of a exoplanet passes through the thin veil of atmosphere of that planet, and then certain wavelengths of light are absorbed by the presence of gases and compounds in the atmosphere. And with great accuracy, James Webb, through this technique called infrared molecular spectroscopy, can tell us what is the composition, what are the molecules that are present, and in what concentration relative to one another. Now, the further away the planet and the dimmer the light of the star, there are things which may have some impact on exactly how accurate and precise the measurements are. But for the most part, they're very accurate. It's going to be able to identify different compounds and their relative concentration. So it's quite good. It's quite accurate instrument.
Okay. So maybe if we don't have other questions, we can close.
Yeah, I guess that's it. No more questions in the chat. So I don't know if anyone would like to add some closure notes or.
Just one thing is
Yes, sure.
assuming that this is recorded and will live on your YouTube channel and so forth, if you can send us a link, we'll also share this on our own social media and website, so we can help you extend the reach.
Sure, we'll send it by mail for you.
We can share it here in the chat.
Oh yeah, I'll do it.
Okay.
There you go.
Okay, hold that up.
You did it already.
Yeah.
Right?
Yeah.
Okay, great. Right here in the chat.
Oh yeah.
Wonderful. Great. Well, I hope you enjoyed that, and your audience enjoyed that. And
I'm sure.
Very grateful to Sabina for the opportunity to speak to all of you and your audience, and hope that was interesting.
It was.
Will I see you in Paris?
Thank you.
Bill?
Thank you so much, Bill.
Yeah. What, Sabina?
Will I see you in Paris?
What's happening?
For the spring meeting?
At the spring meeting, possibly. Yeah, depending on the schedule. I was just in Australia for the IAC meeting.
I didn't made it to Australia.
Yeah, it's a long way to go, but it was a great trip, very, very interesting. But yeah, potentially in Paris in the spring meeting. Yeah, for sure.
Okay.
Yeah.
Okay.
Great.
So thank you.
Thank you.
All right.
Thank you very much, Bill, for being with us.
Very welcome. Thanks for having me.
See you next time.
See you.
Bye-bye.
Thank you. Thank you, everyone.
Thank you
Bye.
so much for your lecture, and yeah, we see you next time.
Okay, Sabina, great to see you. Thank you.
Ciao. Ciao.
Bye.